Oh great, it's just me this time. That's nice. My name is Teresa, by the way. I probably should have started with that earlier, but we should get started. So here's the question. Why do we do statistics?
Statistics literally is the foundation of everything, in my opinion. I can't even answer that question because
we do statistics to prove that.
Okay, so statistics is the foundation of everything, and we use it to prove something?
The purpose of statistics is to prove that your results are meaningful. It's to prove that your results aren't necessarily just due to chance. By doing statistics, you want to find out what the probability was that it was due to chance, or what the probability was that your results mean something.
Welcome back to Significantly. Today's video is going to be a bit more technical than what's come before because we're finally going to dive into statistics. But I'm going to try pretty hard to not get us too bogged down in all those like p's or chi-squareds or alpha, all these symbols. They're important, but today what we're going to try to do is understand the meaning behind all that math.
meaning to our math.
Right, and to do that, we're going to unpack the idea that this series is named for. What is significance?
Important.
It could be significant to you in the sense that it's something you care about, or something that you think you're trying to solve something that's important to you.
If they're important, if there's enough differences between the two groups that it's not by chance alone.
So significance does have something to do with importance, but its meaning in science is a little bit more specific than like special or big, and it probably won't surprise you to hear that what significance is actually about is a certain kind of comparison. Where we left off our fruit fly experiment, our scientists had gathered data from two groups of flies, and they wanted to determine if there were any differences between them.
So what we want to know is whether sex deprivation causes flies to seek out alcohol. And the method that we've chosen to determine this was to compare flies that have been deprived sex to flies that have had plenty of sex, but which were otherwise extremely similar. So we've got these two groups, and we gave both groups the same choice, and here are the results. You've seen this table before. It shows the decisions made by sex-deprived flies, and here's a table showing the choices of the thoroughly mated flies. When you look at the two groups, it seems as though the range of choices each made are pretty different, but how different are they? Exactly. Remember, each table represents a sample, 20 flies or so, and samples always have variation because they come from a population that varies. So how do we know that the differences between these two samples aren't just due to the way that samples vary randomly? Well, actually, we can use that random variation that we expect is going to be present in any population as a sort of baseline. Remember, this green normal curve represents the range of variations that we can expect to see throughout the entire population, and we can compare it to our measurements down here to draw conclusions. When we compare our samples to the normal curve, do they look like this, or do they look like this? If our two datasets form separate peaks, that's evidence that there is a difference between the two groups. But if they form one big peak, then there probably isn't a difference between the two groups. If our data looks like this, then the technical way to describe it would be to say that it fails to reject the null hypothesis, this distribution here being the null hypothesis. The null hypothesis predicts that any variation that we observe is caused by random chance, and that therefore there's no difference between one group and the other. For our fruit flies, this would mean that the null hypothesis would predict that all males, regardless of their sexual history, have the same food preferences. Now, this might seem like a kind of backwards hypothesis to make, because typically when scientists do experiments, they do them because they think that there is a difference between the groups that they're studying, but focusing on the null hypothesis, which predicts no difference, actually makes some good sense. See, science never works by proving anything. Quite the opposite, actually. Science works by falsification. So rather than trying to prove that sex deprivation causes alcohol preference, we can instead show that the null hypothesis, which claims that there's no difference between the two groups, is extremely unlikely. How do we evaluate the null hypothesis? With statistics.
So why do we use statistics? So we use statistics to see the relevance of our data, to see how two things relate, or multiple more than two things, how they relate to each other.
So statistics is the zooming in part, the part that you can see this bar graph, you see that there's differences, but statistics is what helped us know that there is a statistical difference between those two things that wouldn't necessarily be visible just by looking at a graph.
The important idea here is that if you're trying to compare two different things, it can actually be quite difficult to really see just how different they are unless you have some sort of like baseline that you can compare both of them to. And the baseline of the universe, the thing that we should expect to see if nothing else were going on anywhere, is randomness, right? But randomness has certain properties. It takes on patterns and shapes, and we can compare our observations to those patterns if we want to measure how random they are. Let's go back to the experiment and see how it's done.
What we do is we take all of our data about the choices that the flies made, and we run it through a mathematical function called a test for significance. There are many different kinds of significance tests for different types of data. You might have heard of t-tests or chi-squared, but what they all have in common is that after the function is applied to our data, they produce a value called p.
What is P?
What is P?
Yeah, what's a P value?
Oh, I was like, a letter or urine? So a p-value is when you're trying to say how significant your data is, and you choose 5% of the total to say that that's the, oh gosh, no, I just did this in stats.
The technical definition of p is that p equals the percent chance that you would get the results that you did if your null hypothesis were correct, and chance alone was responsible for all the variation that you saw. In the case of our fly experiment over here, p represents the percent chance that we would select the samples that we did if, in actuality, there were truly no difference between the sex-deprived and thoroughly mated flies in their preference for alcohol. In other words, p is the probability that our data match the null hypothesis. The scientists reported in their paper that rejected isolated males exhibited higher ethanol preferences than mated group males. P is less than 0.005. That means that there's less than a 0.5% chance that the scientists were wrong in making this conclusion. 0.5% means that if they repeated this experiment 200 times, one of those times they wouldn't be able to find a significant difference between the two groups, but the other 199 times, they would find a difference. Tests for significance will always produce results like this, where the value of p doesn't actually tell you if your hypothesis is correct. Instead, it tells you how likely it is that your conclusions might be wrong. The smaller p is, the less likely it is that chance alone could have produced your results. So, how small does p need to be to make a conclusion? Well, it depends.
It depends on what your alpha value is, like what value you think is critical enough to say, like, if this is a 5% chance of happening in real life, then we can say it's significant, or like a 1% chance, and it differs depending on what you need to study.
Ultimately, whether or not something gets labeled as significant is going to be determined by human preference, even in science. But it's not determined by, like, my preference or your preference, but rather by norms of accuracy that generations of scientists before us have agreed to.
Different disciplines set different thresholds for significance, which are designated by the letter alpha. Most biological experiments, including this one here, follow the norm of setting a significance threshold of alpha equals 0.05, which means that there needs to be a less than 5% or 1 in 20 chance of getting these results under the null hypothesis in order for significant conclusions to be drawn. Let's put it this way. Alpha is our target and P is our shot. How close did we get? Well, since our P in this experiment, which is 0.005, is much less than our alpha, which is 0.05, there's one less zero in this number than in this number, so we can conclude that our results are statistically significant. That means that if there were actually no difference between the two groups, then selecting the samples that we did would be quite unlikely. It would happen far less than 5% of the times the experiment was repeated. And this means that we can be confident in our conclusion, which is that the differences between the two groups were not caused by random chance, but were in fact caused by the way that flies respond to sex deprivation.
So, after comparing a whole bunch of flies and comparing their groups in this very specific way, the scientists found a significant difference between the groups. So, what does this mean? Can we really say that we've proved that sexually frustrated flies are drowning their sorrows in alcohol or something like that? Well, what does it mean to prove something anyway?
I think maybe one of the first things I learned about science is that science doesn't really prove anything.
I think in science the word proven isn't even a thing.
We tend to think about knowledge like it's this kind of clear-cut thing, like that claims can either be proven true or they're proven false. But when you look more closely, what you find is that assertions like these are actually made up of layers and layers of maybe and probably. And so we've built this language of statistics so that we can better communicate with each other about what kinds of possibilities exist in the world and what they're like. Saying that the difference between the two groups is probably not due to chance might not be as simple and satisfying as like, horny flies get drunk. But like, in many ways it's a lot more meaningful.
I guess what we'd say is to make sure your results are meaningful and you're not just showing what we already know, that there is random variation in the world, that your results indicate that something else is going on.
It's saying that there's actually something very different going on right here, and you might not be able to see it otherwise.
I don't know, man.
These are like some serious, like, opinion-based questions.
Science has always been a practice done by humans, and as much as we might want to remove our opinions and biases from the process, they're still there in the background. So the concept of significance helps us distance ourselves from those biases a bit so that we can decide together what we think is true, based on math and evidence. So if we start with an understanding that the world is varied and full of differences, but nonetheless open to careful comparison, then maybe we can learn something significantly. So, that concludes this series on significance, and now we are finally in a position where we can answer this question. What does it mean for something to be significant, and why should you even care? I'm really curious to hear what you think, so let me know in the comments. Why would we spend so much time laying out this concept? Like, how is it useful? And more importantly, how can statistical significance help us think together about this very complicated world that we're all living in? So complicated. So let me know in the comments what you think significance is and what you think the best ways are to use the idea. I'm really looking forward to chatting with you, so I will see you down below. Okay, farewell!